Exponential graphs have two basic shapes. When the function represents exponential growth, the graph will be increasing. This means as we move from left to right, the value of f of x, or y, gets bigger. When we move from left to right, the graph increases. We know that f of x equals 2 to the x and f of x equals 5 to the x are both growth functions. In this case, b equals 2. Here, b equals 5. My value of b, my growth factor, is greater than 1. So these are both growth functions, and our graphs are increasing. We also have exponential decay graphs. When our function represents exponential decay, our graph will be decreasing, meaning as we move from left to right, the value of y or f of x gets smaller. F of x is getting smaller. This occurs when our decay factor, b, is between 0 and 1. So it's a fraction or a decimal between 0 and 1. F of x equals 25 hundredths to the x, and f of x equals 75 hundredths to the x. Both have decay factors b between 0 and 1. So these both represent decay. Our graph then will be decreasing. Notice that both growth and decay graphs are curved. They're not straight lines. So growth graphs get steeper, decay graphs get flatter. You should be able to distinguish between a growth or a decay graph and a linear graph. A linear graph will be a straight line. While we're at it, you should be able to identify that a graph that's a parabola should be matched with a quadratic function rule. Likewise, a V-shaped graph will be represented by an absolute value function rule. The basic shapes of each of our function families is something you should be really familiar with. Back to exponential graphs. Often we can use our start value to distinguish our graphs or to match our graphs with their function rule. Remember that the start value a tells you the y-coordinate of the y-intercept. However, for each of the examples on this page, we have the same start value, and it's actually a little bit confusing. The start value is not 2 or 5. 2 and 5 are the growth factors. The start value is not 25 hundredths or 75 hundredths. Those are the decay factors. Each of these function rules has an invisible start value, and that invisible start value is 1. This is actually f of x equals 1 times 2 to the x. F of x equals 1 times 5 to the x. F of x equals 1 times 25 hundredths to the x. And f of x equals 1 times 75 hundredths to the x. Each of these then has a y-intercept of 0, 1, since my start value is 1. I can't use that information then to distinguish or to match the function rules with the graphs. Y-intercept of 0, 1, y-intercept of 0, 1, y-intercept of 0, 1, and y-intercept of 0, 1. I've already talked about how I can determine that f of x equals 2 to the x and f of x equals 5 to the x will be matched with increasing graphs because b is greater than 1. And here, these two bottom function rules, f of x equals 25 hundredths to the x and f of x equals 75 hundredths to the x, will be matched with decreasing function rules because of the decay factor between 0 and 1. How, though, do I distinguish between f of x equals 2 to the x and f of x equals 5 to the x? Well, for our first function rule, f of x equals 2 to the x, we are repeatedly multiplying by 2, times 2, times 2, times 2, times 2. However, our output for the second function rule is being increased by a factor of 5. So times 5, times 5, times 5. When our b value, our growth factor, is larger, as in the case of 5, we are growing faster. Our growth factor is bigger, our growth is faster, and therefore our graph will be steeper. A smaller value of b, a smaller growth factor, indicates slower growth, and our graph will be flatter. When I look at these two function rules, I know my growth factor for the second function rule is larger, 5 is larger than 2, so my graph will be steeper. When we get to decay, the opposite is actually the case. A smaller decay factor, a smaller b, is actually a steeper graph. A larger value of b, a larger decay factor, is a flatter graph. Let's think about why that is. In this first case, with our smaller b, we know that 25% remains. That 25 hundredths tells us that says remains, tells us that 25% remains. 75% goes away. A lot is going away. I'm decreasing by a lot as I move from left to right. However, in the case of a decay factor of 75 hundredths, 75% remains. A lot remains. Only 25% goes away. Only a little bit goes away. Therefore, when my b is smaller, I have a smaller amount, a smaller percentage that remains, a bigger percent goes away, my graph decreases faster. When I have a larger b, I have a larger percent that remains, a smaller percent goes away. That means I'm decreasing slower. That last part is really challenging, and I'd like you to really think about it. But the big idea here, growth, increasing. Growth happens when my growth factor is bigger than 1. Decay, decreasing. Decay happens when my growth factor is between 0 and 1. That's when I have a decreasing graph.